Okay. Hello. Do you guys have any questions before I start?
Dr. Foley. So I was wondering, I don't know exactly how to explain it, but like when we were deriving like the units for like integrated rate laws and that kind of stuff, do you think we can go over that today?
Sure.
It's-
So, um, when are you talking? So the units for the integrated rate law?
I don't remember exactly what it's called. I think it was in one of the module videos. I can find it if you need me to, but it's like trying to find like TS of -1 and that kind of stuff. I can go and find it.
Yeah, because I mean, with the integrated rate laws, you only have three options. So you have your zeroth, your first, and your second. So those are really easy. With the zeroth, your K is equal to molarity divided by seconds. With your first, your K is equal to seconds to the -1. And for your second, your K is equal to seconds to the -1, molarity to the -1.
Okay. I can go and see and get a better explanation of what I was talking about.
Okay. Now, I mean, if you have a general rate law, your rate is equal to K A to the M B to the N C to the P, something like that. Your rate is in units of molarity per second. And then each of your concentrations are in molarity. So you have essentially molarity 1 minus M minus N minus P. So your unit for K would be S to the -1. And then if you have M equal to 1, N and P equal to 0, then you just have molarity 1 minus 1, which would cancel that to a 1. If you have M equals 1, N equals 1, P equals 1, something like that, then you do M 1 minus 1 minus 1 minus 1, which would be M to the -2.
Okay, yeah, this is what I think I was talking about. Yeah. This is general rate laws, right?
Yes, this is general rate
Okay.
laws. Make it a little more obvious that that's a 1 as opposed with a L. Okay, so is that all you're talking about?
Yes, ma'am.
Okay, perfect. Okay, any other questions? Okay. Oh, yeah. Okay, so today I was mostly just going to go over what we learned this week, as this is just our weekly review. And then on Monday, I'll do the actual test review. But if there is anything else that you guys want me to go over after I've gone over the stuff for this week, just let me know. Okay, so for this week, we're going over the N part of equilibrium. So we were looking at the reaction quotient. Which is our Q, right? And our Q essentially gives us the status of our equilibrium. process. So a Q that is greater than K, we have too much products, we need to shift towards reactants. A Q less than K, we have too much reactant, not enough product, so we need to shift towards products. And then Q equal to K, we are at equilibrium. With Q, we want non-equilibrium values. So non-equilibrium concentrations or pressures. Okay. If we do have a Q that is greater than K, we will have negative X on reactant side in an ice table. Sorry, on the product side. So if we have too much Q, then our product side will get the negative. If we have too little, then it's going to be a negative X on the reactant side. Okay. And another thing, you can only calculate Q if you have concentrations or pressures for all species in the gas or aqueous states. Okay, so if you have something that you're starting out with 0 of, then you won't calculate a Q for it. You already know which direction it needs to go in. It's going to go towards the thing that doesn't have any. We have to have some amount of every single species at equilibrium. Okay. So that was a big thing with, there's not a lot in this portion. Then we had calculating equilibrium concentrations. With or given Q. Or it's not Q, given K, C or KP. I feel like this is something that it's good to see several times. So I'm just going to go ahead and find another example of this because these do take a lot of time and it's always nice to have something to refer back to. Okay. See what I got here. Dun, dun, dun. Okay. Let's try this one. Okay, so we've got the following reaction. Why is this not reading? What's going on? There we go. Oh, that's why. Okay, so following reaction, H2O2 goes to O2 plus H2, and these are all in a gas state. And we have a Kc value for this equal to 0.0076. We're going to start out with 0.600 molar hydrogen peroxide, 0.400 molar O2, and 1.000 molar H2. And we want to go through here and figure out what our equilibrium concentrations are. So we're going to set up our rice table. Okay, so we need to first know which direction we need to go in. We are unsure right now. So we're going to put these concentrations into our Q. So we have Q is equal to 0.400 times by 1.000 divided by 0.600, giving us a value of 0.667. This Q is greater than this K, so we need to go towards reactants. So we're going to do a minus X on our product side, a plus X on our reactant side, and we get 0.600 plus X, 0.400 minus X, and then 1.000 minus X. This can then be put into our equilibrium expression. So Kc is equal to O2 concentration times by H2 concentration divided by H2O2 concentration. So we have 0.0076 is equal to 0.400 minus X, 1.000 minus X, and then 0.600 plus X. So we're going to FOIL the top and multiply across, so we get 0.0076 times by 0.600 plus X, and this will be equal to 0.400 minus 1.400 X plus X squared. Multiplying across, we get 0.00456 plus 0.0076x is equal to 0.400 minus 1.400x plus x squared. And now we're going to subtract. We want to get everything on one side, so we're going to subtract 0.00456 from both sides. And we're going to subtract 0.0076x. That will give us a 0 on the left side. And on the right side, we get x squared minus 1.4076x. Plus 0.39544. So this is a 1 for our A, then that's our B and our C. So we get negative 1.4076 plus or minus the square root of negative 1.4076 squared minus 4 times by A and then times by C. All divided by 2 times by A. This gives us 1.4076 plus or minus the square root of 0.3996, and it's all divided by 2. So this gives us 1.4076 plus or minus 0.63212 divided by 2. At this point, we can solve. These are all x equals. So now we can solve for our two options. So our x is going to equal either 0.388, or I guess 877, or 1.01986. Now, we have to go back to here. So we have our concentration of H2O2 equivalent to 0.600 plus X. Our O2 concentration equivalent to 0.400 minus X, and our H2 concentration equivalent to 1.000 minus X. We can see that this one right here, if we subtracted it from either the O2 concentration or the H2 concentration, we would get negative concentration. So this one is out. So we're just going to go for the other two. So it's going to be equal to 66 plus 0.3877, giving us 0.988 molar. Then we have 0.400 minus 0.3877. Giving us 0.012 molar, and then 1.000 minus 0.3877. Oh. Yeah, that was right. Giving us 1.388 molar. And then our check. Take our, oh. I added that together, didn't I? Sorry about that. This is 0.612 molar. Okay, so we get 0.012 times by 0.612 divided by 0.988. And this gives us a value of 0.0074. Our actual KC was 0.0076. That is pretty close. So we have confirmed our X is valid. Okay. I just wanted to go over one of those examples. Okay, the last thing that we went over this week is Le Chatelier's principle. So this is the idea that a stress applied to a system will shift its equilibrium position to counteract the stress. Okay, and we can think about this in a Q versus K type situation. So our first stress that we can apply is adding concentration. Or yeah, what's concentration? So let's say that we have N2 gas plus 3H2 gas in equilibrium with 2 NH3 gas. Let's say at equilibrium, our concentrations are 0.250, 0.350, and 0.750, something like that. So we could solve for our Kc by taking 0.750, squaring it, dividing it by 0.250, and then 0.350 cubed. And this gives us a Kc value of 18.4. So let's just assume that that is actually correct. And let's say that we add 0.100 molar, and these are all molar, of our N2 to this system. So now we have 0.750 squared divided by 0.350 and 0.350 cubed. This would give us a value, a Q value equal to 13.1. We can see that our Q is less than our K, which means we need to shift towards products. And that's exactly what Le Chatelier's principle tells us without so much math. If we add a substance in an equilibrium, so one that exists in the equilibrium, we're going to shift away from it. So our forward, in this case, our forward reaction would be favored for a short period of time until we reestablish equilibrium. So if we add something here, we're going to shift in that direction. Okay. Same idea as if we subtract something. I won't do the math this time, but let's say we remove a substance that is currently in an equilibrium. Keep in mind, if we add or subtract something that's not actually part of the equilibrium process, this will not affect the equilibrium. So unless it actually affects concentration or partial pressure, adding or removing something that's not part of the equilibrium won't have any effect. So if you remove a substance that is currently in the equilibrium expression, you're going to shift towards that. Shift towards the substance. So if instead we decide to, or if we removed some H2, we would shift back towards products to produce more of our products in general. Okay. Those are the pretty easy ones to understand. The other ones are a little bit harder. So changing pressure, volume, and temperature. So if we have the following reaction, so we have the same reaction, so I'm too lazy to write another one. And let's say this has a delta H of -12 kilojoules per mole. From this information, we know this is exothermic. And because we are releasing heat, we would say that heat is therefore a product. So same idea as before. If we add something, so if we increase the temperature, of the reaction, that is going to be essentially adding heat. And by adding something, we want to reach back to equilibrium, so we will shift away from it. So that will produce more products, or sorry, more reactants. Now, this will actually have an effect on our K value. So if we add heat, and instead of having our, where did it go? Up there it is. Instead of having these concentrations right here, let me actually. So instead of starting out with these concentrations, now let's say, or let's say we still start out with these concentrations, but now we increase the temperature of the reaction. that's going to cause a shift. So let's say that we end up with 0.350, 0.450, and then I guess technically that would be let's do that a little differently, sorry. 0.300, 0.500, and then 0.650 molar. So by increasing our temperature, we're going to shift away from the NH3, produce more N2 and H2. Now, when we look at our Q here, or we look at our new K value at this temperature, I just put in the wrong values, didn't I there? Sorry about that. Now we get a K value of 11.3. So by adding heat, to an exothermic reaction, we have decrease the K value. And that's because this is going to favor the, that increase in heat is going to favor the reactants more. So this will have an actual effect on our Kc value. Okay. Next is looking at changing the pressure. Okay. So again, we're going to stick with the same exact reaction because why not? Now we're going to go with partial pressures instead. So let's say we're at 0.150 atmospheres, 0.200 atmospheres, and 0.350 atmospheres. Now let's say that this is at equilibrium. So our Kp here would be equal to 0.350 squared divided by 0.150 and then 0.200 cubed. Giving us a Kp of 102. Now, let's say that we increase the pressure on this entire system. Going to increase pressure. So we can increase pressure by either decreasing volume or adding an additional thing that wasn't already in there. And when we increase the pressure, keeping in mind that our partial pressure, so our partial pressure of N2, for instance, is equal to the mole fraction of N2 times by the pressure of the actual system. So if we increase this term, we're going to increase our partial pressure of each of the species. So all of these species are going to go up in partial pressure. So here we're going to have 0.450 atmospheres. 0.200 atmospheres, and then 0.350 atmospheres. This will be cubed and squared.
Is the PATM also known as the total pressure?
This is either, so this is total pressure or atmospheric pressure.
Thank you.
No problem. Okay, so when we solve for this, we get a value of 23.6. So our QP is less than our KP. So we would need to shift towards our products in order to get reestablished equilibrium. So what has happened is we are shifting away from the side with the greater number of gas moles by increasing our pressure or decreasing our volume. So an increase in pressure which is the same as a decrease in volume. So they will have the same effect because remember thinking about PV equals nRT, our gas constant. These are going to be inversely related. So as you increase pressure, you're decreasing volume, or decreasing volume is increasing pressure. So they're going to have the same effect either way. So doing this will cause us to shift towards the side of the reaction with fewer moles of gas. In order to get back to an appropriate ratio of pressures. Because we can think of pressures just like we do concentration in the eyes of an equilibrium. As a note, if the moles of reactant are equivalent to the moles of product, there'll be no shift. So there'll be no appreciable shift in this because both sides have the same pressure. Now, the inverse is true as well. So if you decrease pressure or increase volume, this will cause you to shift towards the side of the reaction with a greater amount of gas moles. And the last thing is adding a catalyst. So if we add a catalyst, essentially we are taking a reaction and we're not doing anything about the energy of the products or the reactants. We're just going to decrease the energy of the transition state. So these right here are the transition states. So adding catalysts, this decreases the energy of the transition state. And when you decrease the energy of the transition state, that decreases the activation energy. Now, as a note, that's going to decrease the activation energy in the forward and reverse processes. So because we've decreased the forward and reverse activation energies, but we haven't done anything to the actual equilibrium, this will have no effect on equilibrium. All that happens is that equilibrium is established quicker. And that's it. And that is everything from this week. Do you guys have any questions? Anything in the last like 5 or 10 minutes that you'd like me to go over?
So the very first problem that we did, if we were given the molar concentration, but for example, if we were given a problem like the moles, we would have to convert.
Yes, if you're given moles, you have to convert into molarity.
That's all. Thank you.
Okay. If there are no other questions, then that's it for today. I will do a full test review on Monday at 3. Yeah, that's about it. Let me know if you guys have any questions over the weekend and have a great weekend. Bye, guys.